Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection as usual. Today I would like to talk about infinity again. So infinity is always complicated, and here's a really good example why you should be careful when you think about infinity. Well, it actually was a very good example, and then something happened. We'll see. But it's a fun problem. It's a coloring problem, but not a finite coloring problem, a very infinite actually. So it's basically about the chromatic number of the plane. So how many colors do you need to color the plane? Basically, that's what it is all about. And it's one of these classical questions where nobody really knows the answer to. The answer is, well, probably a bit weird, or it might be a bit weird. We'll see what it is. So let's have a look. Again, warning, everything is infinite. You should always be careful when you treat infinite things. In this case, infinite graphs. But in general, just infinity is just very, very large, which is kind of a problem of infinity. Anyway, it's also a bit crazy, of course. So basically, 4 colors suffice. Not really. How many colors suffice? So motivated from the 4 color theorem, 4 colors suffice, we would like to color the plane itself. And I just write E2 because there will be some distance involved, and it should be just the usual distance, so Euclidean space. So this is really just r squared. So just all points of r squared, we want to give them a color such that 2 points that are unit distant apart, this is where the distance come in. So here, unit distance apart, they should get different colors. And now I was very stupid. I gave them the same color. Let me just give them different colors. So this one is whatever, blackish, and this one is whatever it is, purple. So that's good. And whenever there's another point unit distant apart, it can be red, for example, and so on. So we just want to color. The coloring problem here is adjacent points get different colors, where adjacency here is now, so you get an H if you are a unit distant apart. And okay, sounds like a fun problem. It's probably not a very important problem, but at least a fun problem to kind of find this, the minimal number of colors that suffice. Right now, it's not even clear to me whether there is a minimal number or whether you need infinite amount of colors. We'll see actually what we can do. We definitely need at least 2 colors, because there will be some point, let's call it 0 in r squared, and there will be some other point, let's call it 0, 1. Sorry, 1, 0, and they're unit distant apart. So we definitely need at least 2 colors to color the plane. Okay, so here's the fun problem. It's kind of an infinite coloring of an infinite graph coloring problem. So like this picture here, there's a huge graph with vertices being the elements of r squared and a lot of edges. And we would like to find the minimal number of colors that suffice. So what can you do? Well, maybe we go for a lower bound and an upper bound. So as I said, a lower bound, well, we already have one. 2 is definitely a lower bound. 2 is certainly smaller or equal than chi of e squared. So e squared again, Euclidean space. But an upper bound, not so clear. And the lower bound 2 is probably very, very optimistic or pessimistic in some sense. We probably can do better and get a much better lower bound. Okay, so finding a lower bound is kind of fun. It's actually a finite problem in some sense, because the only thing you need to find is a finite graph, which is a unit distance graph. So it's only a very tiny part of your plane, but all the vertices, if you embed the graph into r squared, so this secretly sits in r squared, are still unit distant apart. So here's an example of such a graph. All edges in this picture are supposed to be unit distance. So whatever our graph of the plane is, the infinite one, this will be a subgraph. And if this thing needs whatever x colors, then whatever our big graph or infinite graph is, we at least lower bound need whatever kind of many colors, how many colors I need for this one. It turns out this one needs 4 colors. So we definitely then know that the lower bound or lower bound for the chromatic number of the plane, so this guy here is called the chromatic number of the plane, is at least 4, right? So I have to say it again. This graph needs 4 colors, something you can easily check. And it's a unit distance graph, so it embeds into R2, and all edges are unit distant, so a unit apart, so all edges are of length 1, and it needs 4 colors. So this is the subgraph of our big graph, needs 4 colors, so we at least need also 4 colors. We probably need more because there might be a lot of other unit distance graphs here, which might need 4, 5, 6, or whatever, how many colors. But this is at least a lower bound, right? So kind of use this lower bound, a very finite problem, find those unit distance graphs. It's not really a finite problem in the sense that you need to check a finite number of graphs. There's still infinite graphs to check, but each graph, in the end, if you find one, it is finite. So here we have, can I count 10 vertices apparently? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you need 4 colors. Well, this is strictly speaking, what I show you is the 4 coloring, and you need to convince yourself it's a very finite problem, 10 vertices, that you can't do better than using 4 colors. And here now the usual coloring is just adjacent vertices need to get different colors. So this one is green. So for example, here's a triangle, which already shows that we need 3 colors. So triangle is a good way to see that we need at least 3 colors, and you need to get a bit more. Well, it needs to get a bit more sophisticated here to see that you need 4 colors. And it was kind of known for a long time. So the problem is from the mid of the last century, and this construction. There's several of those where you need 4 colors and unit distance graphs, and this was just the easiest one. If you think about it for a while, you might come up with this. It's not super hard in some sense, but still it takes you a while. It's not like you just write it down immediately, or at least I can't write it down immediately. The upper bound is also very funny. So a priori, it's not even clear whether a finite number of colors suffice, but the hexagonal coloring, the hexagonal tiling of the plane, tessellation, which needs clearly 7 colors, or you can use it with 7 colors. You can use that actually to construct the coloring of our graph. So basically what you do here is you have these little hexagons, and each one is slightly smaller than one in its diameter. And then it gives you a coloring of the plane. For example, if you're here, and then all other points a unit distant away will be somewhere in those other, whatever, in the bluish one, or in the purple one, or in the yellow one, or whatever. But they won't be in the green one by construction because the diameter is slightly less than 1. And you piece everything together into a coloring of the plane. So we get an upper bound because you need 7 colors here. You at most need 7 colors. That's pretty cool. So then now we know that 4 is a lower bound, chi, and the upper bound is 7. That's not so bad. So it looks like people came up with this quite quickly. So this tessellation is of course well known. You play a little bit around and you find this one. So maybe it's actually not so hard to determine the precise value. Turns out that it is very hard. So as far as I know, in 2022, this is still an open problem to determine the precise number here between 4 and 7. Not quite, because there was a breakthrough quite recently. So this was our 4 graph, link it in the description. There is a whatever kind of graph which has a, well, here you go. It's a graph. It's a unit distance graph with a lot of vertices, and it needs actually 5 colors. So this improves the lower bound. So my original theorem here, this is the theorem, is now improved to 5 is as a lower bound here. And as you can see, I can't see anything in this graph, so it was found by computer. It's not something you write down by hand, which is the whole problem now, because there could be one with chromatic number 6, a unit distance graph, or 7. But how big should it be? Good question. Anyway, so this was a kind of a breakthrough, and it was kind of pushed using the Polymath project. So this international collaboration of many mathematicians working on many problems. Basically, you post a problem and we'll see what comes out. And here, this was pushed down, and I haven't checked the latest result, but roughly there is now a graph with roughly 500 vertices, which is still way too big to illustrate it. But anyway, it's roughly 500 vertices, and chromatic number 5, which gives this lower bound, which only leaves 5, 6, or 7 to be checked. And maybe you can push it a bit further. Maybe if you run your computer for long enough, you might find a unit distance graph with whatever needs 6 colors, or even 7. If you find one that needs 7, you're good, of course, that you have proven the theorem. But right now, as it is in 2022, as I said, well, we will see. Right now it's just 5, 6, or 7. And the point, before this was found, actually, there was some fun, but it's kind of not so funny anymore because this counterexample was found. So the point was, for a long time, people actually believed that the answer might depend on the axioms of set theory, which is really strange. So, well, maybe not it's an infinite graph, but roughly we had this idea of, well, let's say we are back to this case here. So it could be 4, 5, 6, or 7. And basically what it is if axiom of choice, if you assume axiom of choice, you can do with 4, and otherwise you need one of the others. That was the statement, and was a proof. Was a proof of that statement roughly in 2000-ish, 2003 or something. Link to everything is in the description. And this came way later, so this kind of rules out this case. Anyway, let me tell you roughly the story. Okay, so the axioms of set theory, there's this famous axiom of choice, which looks very harmless. It's basically you have an infinite number of backs, and there is a choice function which selects one ball from each back, and that's the whole axiom. Looks very innocent, is not really innocent. It's one of the most craziest axioms ever because it looks so innocent and then it has some really strange implications. Here's one. So you can construct a unit distance graph, not the coloring of the plane graph, a different one, which works as follows. So again, the edges are, the vertices are squared, so Euclidean space. But now you want not just unit distance, but you also want, so you put an edge only if the vertices are a rational number apart, right? So 0 and 1 are good. So 0, 0 if you want, and 1, 0. But if they're not a rational number apart, so in both coordinates, then you don't put an edge. So this is actually a smaller graph than the one we had before. And there's a theorem which roughly states the following. And this is pretty surprising theorem, link is in the description. So if axiom of choice holds, then you can color this graph actually with 2 colors, which is a bit ridiculous. And if it doesn't hold, so if you assume, or basically I should have written, if you assume the axiom of choice, then 2 colors suffice. And if you don't assume the axiom of choice, you need at least 3 colors. And well, 7 is still the upper bound by exactly using this little picture here. And that's a really weird result in some sense. And people believe that something similar is true for the chromatic number of the plane. And as I said, you can prove that with axiom of choice and under the assumption that this beast or something with chromatic number 5 doesn't exist, then it would be the same. It's 4 with axiom of choice, and it would be 5, 6, 7 without axiom of choice. Sadly, this is now ruled out, which is not saying that the answer to the original question also might still depend on the axioms of set theory, but it's, well, this was really a breakthrough. It kind of kicked out this kind of possibility, which is a little bit sad because it makes my video less interesting in some sense. So I say it again. So people for a long time, at least some, of course, believed that the answer to the original question might depend on the axioms of set theory. And then there was this bummer that, or the breakthrough, however you want to call it, that was kind of ruled out in some sense because this unit graph of this graph of distance 5 was found. And most people, as far as I understand, believe now that the answer is probably 7. So this is probably the coloring, and that's the only thing you can do. So what you need to do basically is you need to push computers a little bit further, or you're very, very smart and you can write down a unit distance graph which needs 7 colors. Anyway, so I would like to have wrapped up this video by, oh, by the way, the answer depends on set theory, but it's not quite true anymore because, well, not quite true anymore, because 4 years ago, someone found, link is in the description, found this unit distance graph, and the original statement of 4 if the axiom of choice holds and all the others if the axiom of choice doesn't hold, doesn't work anymore because that assumes that such a graph doesn't exist. So there you go, but still kind of the little bit smaller example at least hints that something funny is going on with the set theory axioms here. And that's the whole point somehow, because we have now an infinite problem, and infinite problems can be very complicated. So as I said, the guess that probably most people would have or would sign here is that the chromatic number is actually 7 and the hexagonal coloring is exactly what you need to do. But we don't know, it could be 5, 6, or 7, and it might even still depend on the axioms of set theory. We simply don't know. Anyway, I hope you enjoyed the axioms of set theory. Sorry, I hope you enjoyed this video, and I also hope to see you next time.